הכלל אם אין פה מישהו עושה כמו מורה
יצא לי שאין דובר אמת, התאמנתי שנה באנגלית. זה יהיה באנגלית.
אבל כבר באמת באנגלית.
אני כבר התאמנתי על האנגלית פשוט.
So today's speaker is going to be Masada Tzabari. This is going to be her thesis, dissertation, and good luck.
So, hello, welcome everyone. I'm very happy to have you here today to share with you some of the results of my PhD research. Small, short story second first. When I was a little girl, my brother had faith, my oldest brother. He'd walk around everywhere with a small pocket laser in one pocket and a magnifying glass in the other pocket. Now, I was a very little girl, and I remember as a child looking in wonder and magic at all the beautiful things he could do with light and using this magnifying glass, seeing amazing new things. And why am I telling you this? Because when I saw that as a child, I suddenly understood how many things around me I don't know yet, and that are all around us and left to discover. And even in my PhD research, I focused myself on the same way that I did as a child. I chose a subject that for me is that wondrous code of nature that you can't see, but it's there all around us and influencing everything. That is the light polarization. Why do I say that it's a secret code? You can sense intensity of light. You can distinguish between wavelength. You can see different colors. Light polarization is a characteristic of light which we are blind to, and yet it's all around us to find and discover, and influences us all the time. So I chose a few specific settings of marine environments in which I wanted to see effects of light polarization, the pattern of light polarization, and how particles can influence that that pattern. So before we get into our research, I'm going to answer a few short questions as a background to linear polarization, the basic questions that we have to know before we get into this. First of all, what is linear polarization of light? Second of all, how does light become polarized? And third, why are we looking at this? Why do we care about linear polarization in nature? So let's start from the first question. What is linear polarization? If we define light as an electromagnetic wave propagating through time and space, then the way I define linear polarization is according to the orientation of the plane of vibration of that wave. Okay, if I look at a single wave, like I have in this figure here, then this wave is linearly polarized because it propagates on constant plane of vibration. It doesn't change. But once I have a package of many waves, this orientation can change. And so I define the degree of linear polarization according to the ratio of intensity of light that is linearly polarized out of the general the general intensity of the light of the package. Also, I define the orientation of this polarization according to the E vector angle, the angle of the electric wave that I have in this wave. So that's our what. That's what is linear polarization. Now we want to know how light becomes polarized in nature. So in general, any process that light goes through, which is dependent on the orientation of the light, will cause at least partial polarization to to the light that goes through it. And most of the processes that we know of light are dependent on the orientation, such as refraction and reflection. Just an example, when you look at the reflection of light off a sea surface, it will probably be partially polarized. Okay? Scattering. Scattering also causes polarization. For instance, the blue sky that we see from Rayleigh scattering is not just is not the only effect of Rayleigh scattering. We have also a unique polarization pattern of the sky that's dependent on the position of the sun in the sky. And even just transmission through mediums that have dependence of their refractive index on orientation can also cause polarization when light goes through them. So that's our how in nature, and not only in nature.
Can you explain in more detail how, say, reflection causes the light which comes from any direction become polarized?
Well, any light, you can break up the light into components. You have your parallel component and your horizontal component. No, horizontal and what's the word? Horizontal and vertical. Let's say that those are the two orthogonal components of the light. Now, when the light reaches the interface, the refraction and reflection of each component is calculated separately, is defined separately by the Fresnel equations. So each one of them will have different reflectance. Okay? So a different percent of it will be reflected. So partially, I'll have separation between the two components. So one component will be stronger than the other. Okay, so I get a relatively, one component will be polarized, we can call it, to some percent. Okay? Okay, so we did our what's in our house. So now we will, okay. So now to our whys. Why does this interest us? Who does it interest? Okay? So, as I said, light is a specific code. Okay? It's another data channel that we have about light. For instance, in places where the other channels don't give us any contrast from the source that we're looking at. I'll give you an example. Okay, there are creatures in the ocean, not just in the ocean, that are sensitive to polarized light. They can see the difference between different degrees of polarization, and they use this tool. For instance, cuttlefish here use this tool for navigation. They use the pattern of polarization of the ocean. They use it for hunting their own food. The figure here is a polarized figure of transparent animals in the ocean that they eat. Okay? It can cause enhancement of the contrast of these animals so that they can see them and hunt them. They even use them for communication between themselves. Also, we use this contrast. Okay? For instance, I brought here two figures. One is from polarized microscopy, where you see the difference in degree of linear polarization in the different colors. And this figure is from remote sensing, okay? From satellite. A figure, an image through horizontal and through vertical polarization, okay? Because we have, okay, just leave it as that. 1 second, sorry. Now, beyond the fact that this gives us extra data, also the orientation of light itself can affect, for instance, photosynthetic organisms. Research has shown already that there are photosynthetic organisms that can actually orient themselves or their chloroplasts to the orientation of polarized light, which helps them make better use of the light that they receive. So yeah, we care about this. We want to see how different things, different effects can change these patterns of polarization. Also for the biosystems, also for our own, for the data that we want to find out of these backgrounds. Okay, so now that we have the basic questions of polarization, we're gonna go forward to our research. We chose two specific marine environments to look at. Now, the first half of the research is an experimental research. We went and we actually took measurements inside the littoral caves, and we characterized the polarization. Now, I just want to note that such type of research to characterize specific unique settings of light to check their polarization have been done all over the world, under ice caps, in swamps, all kinds of different places that you expect from the light to have specific polarization characteristics. But this is the first time that anyone has tried to characterize polarization in caves. Now, the second half of the research that we'll get to later is about the effect of coated spherical particles and non-spherical particles on the underwater polarization pattern caused by scattering. And this is a model research that we used the same algorithm that Amit used here once for homogeneous spheres, and now we used it for non-homogeneous spheres, coated spheres, and non-spherical particles. So we're going to start with Washanika. And this is inside the caves. And we asked ourselves two main questions that we wanted to answer in this research. First of all, as I told you, this is a unique setting of light. So we wanted to see, does this unique setting of light have a specific characterization of the polarization pattern? And second of all, I want you to notice here, I don't know who's been lately to Washanika, but Washanika, besides its beautiful light and inside cave and water and everything, it's also a very unique habitat for microalgae growth. So you see here on the floor and on the cave walls, we have a flourishing microalgae growth. And this is interesting because even though we have here a lot of humidity, which is great for them, we have very, very low intensity of light. In the months of winter, we reach the peak, at the peak of the day, they have about 6 microangstroms. That's what we measured there. So we want to see how this polarization, if at all, could affect this habitat. So in order to answer these questions, we had to build our own measuring tools. And we used two different techniques, which are built on the same physics. One is the photograph analysis method, and the second we use a spectrophotometer. In both cases, what we actually did is use a filter, polarizing filter, to extract just the components of light that we wanted to use at 0 degree angle that we defined, at 45 degrees, at 90 degrees. Which give us 3 components of light, I0, I49, 45, and I90, which builds the Stokes vector, which in turn helps us calculate the degree of linear polarization and the E vector angle. Is that okay with everyone? Okay. So, I'm going to start off looking at the results of the spectrophotometer method. Now, the spectrophotometer method is basically, and gives us average readings. Okay, it takes a conus of light, okay, and it doesn't give us any differentiation between different processes that the light goes through. It just gives us a cone of light, and on that cone of light, everything together, it gives us an average polarization. That's why we're going to start with it, because we expect that this is actually what the algae on the wall right behind us are seeing, or feeling, or sensing, or whatever. How hard is it for you guys to see what it says there? Okay. So what we have here on top is the degree of linear polarization. Oh wait, I have this. Is the degree of linear polarization. And on the bottom we have the E vector angle. Now we took measurements in 4 different months. In November for our spring, our fall measurements, February for winter, April for spring, and August for summer. And each day that we went, we took measurements throughout the day, 10 o'clock, 12 o'clock, 2 o'clock, and 4 o'clock. And also we separated the polarization according to wave bands. Now, we saw, I'm not going to talk about everything that we learned out of this, but a few important points. First of all, in all the months except for August, except for the summer month, we have our maximum polarization at noontime, and this fits with the Rayleigh pattern. If you'd sum it, you'd get 0, because your main donor to the intensity, the main intensity comes from your direct stuff, which is unpolarized. Yes.
But there is a relation also to the clouds, no?
Yes, there is relation to the clouds. But we tried to take days that we didn't have clouds. Sometimes you do have cloud here and there, but mostly we tried to take it in days that were not cloudy. Okay, next we saw, okay, that's, where were we up to? Okay, summer. Now, in the transition months of November and April, it's interesting to see that you can see both effects. Okay, you can see both the maxima at noon, that goes with our Rayleigh maxima from the sky, and also a secondary maxima towards the evening from our ocean reflection. Yes.
Opening of the cave.
It's opening of the cave. No, the sun, here in these figures, we didn't take the sun when the sun is exactly.
It's not exactly opposite,
yeah.
but the intensity is maximum if the sun is
No.
directed.
Yes, but here we're not looking at the intensity. We're just looking at the polarization. This doesn't give you any information about the intensity. Okay? I can have high polarization with very low intensity, as we see in February. The next point that I want to say. In February, what we see is the highest polarization throughout the year from the measurements that we took. And what's interesting for us is that it comes together with a nearly constant E vector angle. Why do I say that this is interesting for us? Because as I said before, February is the month that we have lowest light intensity. That's the time when the microalgae inside the cave need most desperately light. And I can't check this, I didn't check this yet, but as a continuation of the research, it would be very interesting to look from a biological point of view to see if the algae in the cave actually use this tool that they have here. Okay, so next, as I said, this is an average. These values are average values of polarization, and if we want to see specific processes that the light goes through, then we have to look and use another tool, which is the image analysis method. So what we have here are polarization images and E vector angle images, in which actually we did the same calculation as we did for spectrophotometer method, but on each single pixel. And we can also separate this to the 3 data channels of R, G, and B, so that we can get also data on the different wavelengths. So here we have the R, G, and B rows. We have here the degree of linear polarization for cave walls, and the degree of linear polarization for the far ocean and sky. Why do I separate these? Just because of the saturation of the image that we're looking for data on the cave walls, I get saturation of the light that's far. I had to use two different exposures to get these two different figures. So what do we see here? First of all, we see that the highest polarization that the highest donor, not donor, what's the right word, anyone? Not donor, contributor? Contributor to polarization is the ocean, and also high polarization from the cave walls, which is interesting because the light that they supply is actually very, very low. Into the cave walls, the polarization that they give to their own surrounding might be able to enhance the light that algae receive only from their reflection. This is something that we couldn't see when we looked just at the average polarization from the spectrophotometer. Another thing we couldn't see from the spectrophotometer is in the E vector angle I want to show you, that you can see here for the cave walls, we have two different E vector angles on the two different sides of the cave walls. This is data that is lost when we look at average results. Okay, so now this is really only a qualitative measurement, and of course to get more accurate results, we had to also take the information from there and turn it into summed averages, but this time we could look at specific pixels of the areas that we wanted to look at. Okay, we took specific pixels of the far ocean, specific pixels of the sky, specific pixels of the caves, and made from each one of them averages over for each measurement. It pretty much shows the same information that we took from the qualitative results, but anyway, this is better.
So can you explain how you define the angle 0 of the E vector?
The what?
How you define the angle 0 of the E vector? You have a ray going this way, right?
Yes.
So you can define the 0 angle.
Oh, okay, that's true.
So how you define?
I defined it specifically in the research as not vertical, as vertical to the horizon. Okay. Other researchers have to do it horizontal. Yeah, that's my decision. Now, just another point about this: when we look at the different components separately, we have to remember, as I pointed out before, that high polarization doesn't mean that this light is coming with high intensity. It doesn't mean that it's a high contributor to the overall polarization. For instance, you have here the ratio between the intensity of the ocean and the intensity of the sky. Okay, and you can see that the intensity of the ocean is always lower, even though we said that the polarization is higher. And it also changes between wavelengths. Okay, so the overall polarization, we still look at using the spectrophotometer method and not this method. Are there any questions until here? Because I'm going to go on now to the second part of the research. Okay, thank you. So we're going to sum this up using the same questions that we started with. First of all, we asked, does this unique setting have a unique polarization characteristic? And I say definitely yes. Okay? Because we have a very specific point of view on the polarization from our Rayleigh scattering pattern and from our reflection pattern. So it gives us such a small view of it, gives us a very unique polarization. Secondly, do these characteristics influence the unique bias system that they have? Well, I hope they do, because we found things that could actually help them very much. Okay, we found that in the time of very low light periods, we have very favorable conditions of polarization. And further research can maybe show the connection between them to the microalgae that grows it. So, the next part of our research is the model research, as I said. And since it was a model research, we could allow ourselves to try to take a very wide overview of the effects of structure and composition of a coded particle on the polarization pattern. So what we asked ourselves here, first of all, is how do the structure and composition affect the polarization pattern? And in this question, I'm actually asking also, how important is it that I actually look at these particles as coded particles and not just some homogeneous particle with a mixing rule? And secondly, can such effects be significant to polarization-sensitive creatures or to our own polarized remote sensing? So I hope we'll be able to answer these. In the model that we used, we looked at particles that had 5 parameters that we could play around with. Okay? This is our particle. It has a core and shell configuration. In each one of them, we had a complex refractive index that gave us 4 parameters. And besides this, the 5th parameter is the RCS parameter, the radius of the core to the radius of shell ratio. We used size distribution of these particles according to what Lennon and Karen did for homogeneous spheres. They found was most suiting, but a Young size distribution with this parameterization. And the setting that we used was a smooth ocean surface with refraction and a single scattering of the light from our particles. Now, in order to understand a little bit what we're seeing in this research, we have to go a little bit back to homogeneous spheres. What we have here are patterns of polarization from Rayleigh scattering, Meade scattering, and geometric scattering. We are going to use later on characteristics of the Rayleigh scattering, which are Pmax. It has a maximum polarization. It's the angle of that Pmax and the angles of the 2 neutral points in which we have 0 polarization. And these characteristics are still visible when we take all these different particles and combine them in the Young distribution that we use. You can see here, this is an example of a curve after size distribution, after using the size distribution. Okay. Now, one more thing that that we noticed in our results, but it doesn't exactly apply just it doesn't apply just to coded particles, but I thought it was important, is that Amit in his research used a 90 degrees and used the sun at the horizon in order to enlarge the effect of polarization in backscattering. You can see it here in the blue curve, the blue smooth curve. Okay, that is how light scatters in the ocean after we have refraction from the horizon. The reason he didn't take the zenith angle is because this is how it looks. You see the red or orange, I think it is red. It goes down very smoothly. It doesn't have neutral points. It doesn't have any polarization in backward and forward directions. This is just like Rayleigh scattering in the atmosphere. But what we showed is that if we have if we have structure to this curve, it's not just smooth curve, like you see here in this coded particle. This structure actually stays between different zenith angles. Okay, you can see here in the blue curve, you can see this structure here, and you can see that when I take it down to solar zenith of 0, it stays there and still influences the backscatter. Which is more, and taking this angle is more important for us than the 90 degree that Amit took, because it has higher intensity. I have here also polarization and also high intensity. Whereas when you take low intensity and high polarization, you get high polarization, but there's hardly any light there. Okay, so the point of this is that anything that I take, anything that we show, you can show it in the structures. This will be the same throughout any zenith angle. We still take the 90 degrees, but it's right for all degrees, all zenith angles that you take. Now, choosing the values for our parameter set was not easy. We wanted to take a large overview, and this is one example of what we took. Okay, we took, for instance, constant Ri of refractive index. Let's just call it Ri, okay? Refractive Ri of the shell, and for that refractive index, we took real Ri of the core. We took 4 different values. For each one of them, we took 11 values of imaginary Ri of the core. For each one of those, we took 5 different values of the thickness of the shell. That's a lot of curves, okay? Now, in order to be able to understand a little bit more the tendencies without looking at all these different curves, what we did is take the characterization, what's the word? We took the features, let's call them, of a regular Riley curve, the Pmax, the angle, and the neutral points, and for them we made curves of dependency on the different parameters. So I'm going to show you part of these results. I'm going to start with the Pmax as a function of absorption, both in core and in shell. So what we see here is 2 figures of Pmax as a function, first of the imaginary part of the core Ri, and then of the imaginary part of the shell Ri. Now what I want to show you here, oh, I don't think you can read it. Okay, it says here RCS is 0.9 and 0.95, you can't see that. But what this means is a very big core with a very thin shell. And I'm changing here the imaginary part of that core. And what we receive, what we have here, this very linear function is actually the boundary of a homogeneous sphere with the same dependency. And you can see this again when we move to the shell. Okay, when I change the shell, when I have a very large shell, a very small core, I reach the same boundary. Okay, so those are our boundaries, and now let's see what happens beyond those boundaries. So when I look here at changing the core, I can see that even for very small cores with high absorption, I still get the effect of decrease of Pmax. Here I'm looking at 0.1. I have this in my hand and I'm going to there. I have here 0.1, meaning a volume of, a relative value of a volume of 1 to 1,000, okay? And yet it causes a decrease of the Pmax, okay? And even more, I can say that already at 0.5, which is this green line here, okay, the green line, we already received the exact same identical tendency of a homogeneous sphere with the same absorption. Okay, meaning that it's has a very strong tendency. Now, moving to the shell, what's very interesting for us, and what was very interesting for me to see at least, is that unlike the core, which you say, okay, it decreases a little bit, it gives a little depolarization, here the tendency is even stronger than the homogeneous sphere. Okay, I have a homogeneous sphere here in the red, okay, and here I have a very thin shell. The very thin shell that's very absorbed with high absorption gives a higher depolarization than a homogeneous sphere with the same absorption. Okay, are you going to drink a second? Okay, 1 second. Let it sink in. You'll understand that it's amazing. Next, I looked at the dependency of on the real part of Ri, and it's brought here only the shell because they're nearly alike, the shell and the core. Now you can see here, first of all, this is the tendency of the sphere. This is the, as I showed you before also, that we have the boundary. This is the boundary of the sphere, which is very strong. You can see between 0.4, between 1.4 and 1.65, we have a difference of 50% in Pmax polarization. And also for a thin shell, you can see a very high tendency of depolarization. And also it's very strong, we have a very strong dependence on the RCS parameter itself. You can see here a difference of, this is 0.95 and this is 0.9, and it already gives a difference of 10% in the Pmax polarization. Now I want to show you what happens when I look not at this was a non-absorbing shell. I have only real refractive index, and here I'm looking at an absorbing shell, and the amazing tendency that I showed you here before, a 50% difference, just vanishes, disappears. Okay, you can see that these values are nearly constant throughout the changing of the real part of Ri. Okay? I think that's enough of this. It's interesting, I promise you. Okay? Now I'm going to skip one of these, and after we looked at at a lot of the graphs that I just showed you, all these different overviews of tendencies, we wanted to go also into seeing specific cases of particles in the ocean. The first case that we looked at was air bubbles, and it's an interesting fact that air bubbles, even though we think about them in the context of waves breaking, they actually have a tendency to become stable through coatings adsorbents of a protein film onto them, and they can go down to tens of meters deep thanks to these coatings. Stay stable. So what we have here is our non-coated air bubble in black, and we have a red non-absorbing protein coat, a very thin film coat, and you can see that the difference between the two curves is only apparent in backscattering, entirely in backscattering, and it adds up to 10% difference of Pmax polarization. Why is this interesting? Because this difference comes also with a difference of intensity. It also enlarges the intensity of the backscatter of these bubbles. Why is that even more interesting? Because when we use remote sensing for sea surface color, to calculate phytoplankton, the amount of phytoplankton we have in the water, bubbles usually cause a known error to that calculation. Now, this here shows, this polarization curve shows that after these bubbles go through coating, they actually have a very unique signature in the polarization, which could probably be able to separate the two effects of bubbles and phytoplankton. Interesting. Next specific case is microalgae. Now, I took 4 different models of microalgae. The black one is a homogeneous sphere. The next 2, the pink and the green, are 2 models in which we have an inner or outer chloroplast. The other part would be the cytoplasm. These are 2 models that were used by Laurentis and Bernard. They came to the conclusion that the outer chloroplast is the more accurate one. And you can see that the difference between them here in the polarization is that the inner chloroplast is a smooth curve, while the outer chloroplast, even though it's in the same positioning, gives us fluctuations. Now, why is this interesting for us? Because if this is true, if looking at a homogeneous sphere, which gives us a smooth curve, is not the correct model, then this fluctuation can actually enhance for animals the ability to differentiate, to cause contrast of their food, the phytoplankton, and its surroundings, with what we call a twinkling effect. Okay, where the polarization goes up and down quickly, and when you see it in slight different angles. This twinkling effect has already been shown with intensity that animals use it, and now if we can add to it also the twinkling effect in polarization too, that gives an even more enhancement of their prey. Next, and a final case that we looked at was black carbon, which is a product of incomplete combustion of fossil fuels. And what's interesting about black carbon is that it's been shown that it's been shown to have high quantities in sediments. Means that it has been either absorbed or coated by other particles in the ocean and before sinking. So what I showed here is black carbon absorbed on particulate organic carbon. What I took is actually phytoplankton RI for this cause. So I have here in green, in light green, the average plankton sphere, and in the dark green we have the same sphere coated with a very, very thin film of black carbon. And you can see the difference. So we have here 40% difference in Pmax. We have a whole slant of the whole curve towards forward polarization, and this can change drastically the polarization pattern, since phytoplankton are one of the basic polarizers that cause the polarization in the shallow waters. So this is what I would like to call polarized light pollution. I didn't invent polarized light pollution. I hope that didn't come out wrong. This is for me an example of polarized light pollution. Anthropogenic particles that cause a very big difference in the polarized light pattern. Which can affect the animals that are polarization sensitive, and can also affect the way we remotely sense the polarization from upwelling. So it's an interesting point. So to conclude, we asked how do variations of the structure and composition of coated spherical particles affect the underwater polarization pattern, and how can these affect sensitive creatures or polarized remote sensing. So what did we see? We saw for one the effect of absorption of a coated particle. We saw that even small, highly absorbing components inside the particle can highly affect the Pmax polarization. We saw that thin shells can cause even stronger depolarization than homogeneous spheres themselves. And both of these effects we just saw in the black carbon particle, what we call polarized light pollution. We saw also that changing the order of what's inside and outside the particle can cause effects of on the smoothness of our curve. We saw this effect in phytoplankton, what we called the twinkling effect. We also saw that thin, non-absorbing shells can also change the polarization pattern. And we saw this effect. We saw this effect in bubbles that can cause enhancement of backscatter, also intensity, and also polarization. Together, that's stronger contributor of backscatter polarization. I think that's it for the summary. Now, all you saw here, meanwhile, that's only half of this part of this research on non-spherical and coded particles. We have the other half of the research will become maybe next time on non-spherical particles with the spheroids and their effect on the polarization pattern. So that's it for now. Thank you very much for your attention, for being here to share with me. If you have any questions, I would like to answer. Thank you. Yes?
With the particles that were coated by the black carbon, you had a maximum about 75 degrees. What's the significance of why?
What's the significance? Okay. First of all, wait a second. Okay. Okay. What was the question exactly? Again, sorry. Emacs?
Yeah.
Well, for one thing, we're looking here at light that is entering the ocean. Okay. So when I look at forward or backward directions of the polarization, what I'm actually saying is what will be upwelling and what will be downwelling polarization. Okay, so for instance, if I'm talking about remote sensing, then all my backscatter polarization is contributing to my remote sensing of the upwelling polarization. So if I have movement of this towards forward polarization, then I'm contributing to downwelling, and I won't see this polarization after that. Also for animals, let's say animals are looking for phytoplankton, okay? So this moves their direction from, if they know how to navigate naturally with these particles, using these particles' polarization, then this is tricking them, okay? They're used to seeing their maximum polarization in 90 degrees of scattering. This is changing this around for them. Okay? We're changing their environment, their patterns that they see. Does that answer your question?
Anyway, what about the atmosphere? I mean, if we look at the dust coated by black carbon,
okay, first of all,
we get also the same.
It could. We could check that, but it's not with the same model. It is the same model. It just would have to change the medium that we're looking at. Because here we're looking in the ocean. It could be the same. We could change it. It's something we would have to check. We could next do this whole thing over again in the atmosphere. Yes.
All this part, you said it was a numerical or just simulation? Or?
This is only models, yeah.
So you try to take some measurement with
I'm not really into measurements, but it would be very interesting to show. No. First of all, no, there is a lot of research now about black carbon. I didn't see yet any research about the polarization that black carbon causes.
So we have no validation whatsoever to the result of this?
Nope. It would be nice. We could do that next. Yeah.
But you could say something about the measurements that have been done.
Oh, well, okay, but I don't know if that's actually that. Okay, it is true, and we did talk about this, that there are measurements that show that actually, and I think it's Tunisia, I actually have here which article it was. No, I don't have it here. Okay, anyway, he shows that they did measurements in an area with high chlorophyll, and instead of getting polarization that looks like this with a high Pmax, they get very low Pmax. And they get also these fluctuations in the forward direction, which usually don't come with either with any other particle that we've seen. Okay, this this is very unique with the amount of fluctuation that we have in forward direction. I did think that it might have something to do with that result that they got, but I don't have really a way to validate it. It does connect it to me, for me.
What is the meaning of this outer chloroplast?
Outer chloroplast, as I said, outer chloroplast is really just a way to model the particle, meaning the particle inside. With phytoplankton, we're talking about actually like a living creature. Okay, it changes all the time. It moves inside. So when we try to model it, it's not really just a physical structure that we can say, oh, this is the structure. So they did try to do some changing, some different kind of thinking about how to model it. That was one model that they used. They saw that when they use that structure, it gives the most accurate result of backscatter. So according to that, I thought I also used theirs.
It's not the sphere is coated with chloroplast, right?
No, it's not a thin shell. It's not a thin shell. It's thick. Okay, it's a thick part of the particle. Yeah. Okay. Yes.
Is there any regularity in these fluctuations? I mean, what control the fluctuations?
You know what? I don't know. We saw a few things that affected them. First of all, when we used very, like this case, we're not changing the size distribution, but maybe the effect of it is somehow more important in those particles. Maybe in meek particles, those effects are stronger in those conditions. Yes.
The first part of the measurement, the decades,
Yeah.
how many days in each season did you?
No, it's a single day. It's a single day. I said that these are results that we're hoping to show as. I can't say that they're representative of the whole month, or something like that. They're representative of the day that we went there. We took it in different. Yeah. We were hoping actually to put there, once was an idea to actually place there. We don't have the equipment for this, but there are polarizing cameras that what I did with changing each time the direction of the filter and everything, it doesn't have to do that. It splits the light into three, goes through 3 different filters, and combines automatically the polarization image. So if we had something like that, we were dreaming about just putting it there and seeing what happens throughout the day and night.
Some of your claims, for example, about secondary peak in November, I'm not sure they are significant because the differences are tiny and you don't have any standard deviation or nothing if it's based on a single measurement.
You know what, you might be right. You might be right about that. You might be right about that. That's something that we have to check again, maybe. Yeah.
Do you think that different polarization patterns can be used to identify pollutants, different pollutants?
Well, that's what I was hoping. But, I didn't see enough data in literature about pollutants in the ocean, only in the atmosphere.
Yeah, in the atmosphere.
But I would like to look at them in the ocean. People don't, I guess people care more about the atmosphere, that's true, but everything that's in the atmosphere reaches the ocean in the end. In some way or the other, it reaches the ocean. Any more questions? If no, it's okay.
זה טוב פה. קרוב, לא?
לא, אתה מכיר. אני חושב שמבחינתי זה... תודה.